Okay, first of all, there's lots of events happening in the center tonight. Is everybody here for Tucker Hiatt talking about the world's most famous equation? All right. You are not here to see Klingons, or maybe you're here to see Klingons also, but they'll be here afterwards. All right, very good. I'm Rich Ozer, president of EAS, and there's Dave Rodriguez. He's our program director and has arranged this wonderful talk tonight. So really, I don't have a lot to say other than if you're an EAS member and are interested in the Barcroft High Altitude event, we are going this year in the very beginning of September, sorry. And that is at the Barcroft High Altitude Research Station. We have a week up there, and you can do all kinds of astronomy, astrophotography, whatever you want at 12,500 feet. So it's a great experience if you've never done it before. Anyway, that's really all I had to announce tonight. Dave's got the rest of the announcements, and we'll introduce our speaker. So thank you for attending. Yes?
Read it after I do my little introduction. Yeah, if you can, or you can do it on my phone if you wish.
You mean on the news?
On the newsletter, yeah. Thank you very much. Okay, so ladies and gentlemen, boys and girls, I'm sorry, I used to lecture at Morrison Planetarium, so I always do boys and girls, even though there obviously are no, well, we're all star children, right? I'm Dave Rodriguez, and I'm program director with the Astronomical Society. And I'm also shamelessly self-promotional. So anyway, but thank you very much for coming tonight, especially given the weather. I'm very, very pleased at the turnout for this talk. Tonight is a very special night because tonight is the 100th anniversary of East Bay Astronomical Society. 100 years ago in late February or early March, I'm not sure, was it March, late March? Late February was when we had our first meeting, 1924. And we've gone on and done remarkable things. One of the most remarkable things is all around you. It's the building of this center. This center would not be here if it was not for East Bay Astronomical Society. I'd like to say that we've had a number of remarkable speakers. We've had, by my count, at least 5 Nobel laureates as speakers, including Einstein. Einstein actually visited EAS, but he did not speak to us sometime in the late 40s or early 50s. I'm not sure exactly when. I've been meaning to go into our old newsletters. I'm sure there are records of it there, but I don't know the exact date. Lou, you don't know when that happened, do you? Yeah. Anyway, so I met a number of people who had met Einstein, and as I said at the previous meeting, I have actually sat in Einstein's desk. It's very appropriate tonight that we have a talk about Albert Einstein, as I said, because he's arguably our most remarkable, our most famous guest ever. And I just wanted to say a little bit about, as an introduction to tonight's talk, a little bit about Einstein. Does anybody know what his birthday was? It's totally appropriate. Yes? No. Oh, Pi Day. Yes, it is Pi Day. It is March 14th. Now, when you get a chance, look at the equation for general relativity, and you'll see that pi, it plays a prominent place there. What else did I want to say about Einstein? In his, this is the front page of the paper from which E equals mc squared is derived. And he has a charming first sentence. He says, the results of an electrodynamic investigation published by me recently in this journal, and that was the paper on special relativity, which came out a few months before this, leads to a very interesting conclusion, which shall be derived here. And that, of course, is E equals mc squared. Now, by the way, I want to offer $1,000 to anyone who can find E equals mc squared in this paper. It's not there. It's not even close to being there. Rich, could you skip? Because Rebecca wouldn't let me offer $1 million. Okay. She said I had to specify this very quickly. Can you skip ahead to the next? This paper is only 3 pages long. And he says, at the bottom here, he says, page 2, we can therefore put, next page, please. It's up here at the top, blah, 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 blah. And let's see where it is. From this equation, it follows directly. If a body releases the energy, and it should be L, is the force of radiation, its mass decreases by, it's L over c squared. And that is the closest you get to E equals mc squared in this equation. Now, so you can think of it as delta M is equal to L over c squared. Why does he use L instead of E? I thought it might be L for Licht, the German word for light. That's not it. L stands for Lagrangian, which is something that physicists at the time used to represent energy. I don't know why. I used to know what a Lagrangian was when I was smarter than I am now. Maybe some of you remember. And actually, so Einstein was not the first one to actually write E equals mc squared as the version of this equation. About a year later, I think it was Lorentz actually wrote it that way. He did script E sub 0, and then it puttered along, and Einstein didn't do it for many, many years until finally, next slide, please. 1945, after this happened, he was popularizing the equation, and it wasn't in Time magazine. It was in another, I think it was Popular Science or something like that. That's when he wrote E equals mc squared. And the reason he did that is he realized that people can do multiplication more easily than they can do division. By the way, Einstein hated this Time magazine cover. Can you guess why? Yeah. Einstein was a pacifist. He was anti-militarist. He hated the fact that his efforts had led to the atomic bomb being developed. He bitterly regretted signing Leo Szilard's letter to President Roosevelt. And so he hated this Time magazine cover. By the way, he was on Time magazine cover at least 3 times by my count. One was Man of the Century for the 20th century. So I'm ready now to introduce our speaker. Were you able to find that? Thank you very much. So tonight's speaker, I have thought about doing this talk myself, but people are sick and tired of listening to me talk, understandably. So I was so overjoyed to find somebody who could do a much better job of it than I could. And that is Tucker Hiatt. And let's see if I can. Now, Tucker is the founding director of Wonderfest, the 27-year-old Bay Area beacon of science. After earning his bachelor's and master's degrees in physics at the University of California, which, by the way, is where Lou Epstein, Lou, raise your hand. Does everybody know who? Can you raise your hand, Lou? There. This big round of applause for Lou. Louis Carroll Epstein is a big expert on Einstein himself. I asked specifically for Lou to be here tonight. He wrote a book called Relativity Visualized, which I highly recommend. And he also wrote Physics Visualized. And was it thinking? Shoot. I'm sorry. I have trouble thinking. So thank you very much. And so Tucker taught high school physics for 33 years. He also taught at the Exploratorium and was a visiting scholar in the Stanford Chemistry Department and has won the Amgen Award for Science Teaching Excellence. So without any further ado, Tucker, would you like to come up here?
I would.
Thank you.
Dave, thank you. That's a scary introduction. Thank you very much for inviting me here tonight. I gotta admit that I know 2 people in this audience rather well, and I'm very glad they're friends of mine and they're here. But hearing about Lou Epstein's presence really worries me. The man knows relativity inside and out. He should be giving this talk. Imposter syndrome doesn't do justice to what I'm feeling right now. But as long as Lou doesn't raise his hand and ask any questions, I think we can get through this just fine. I hope you enjoy it. All right. I'm also not using my own laptop here. I'll just actually. Oh, no, that's okay. I'm starting with humor. All right. This is Gary Larson, a classic. And the next the next slide shows just the title of the talk. It really does. Yes. All right. You're going to get very tired of me saying next slide, Richard, but thanks for your patience. All right. There it is. Right place, right time, right subject. Notice the subject is not Einstein. The subject is the equation itself. So let's take a look. But wait, before we do that, next slide, please. How about this question? You've come all the way in the rain, no doubt, from various parts of the Bay Area to attend this meeting. And I urge you to think about why you're here, and perhaps even to enlarge that question to make it apply to the general question of existence. Why are we here? And I think another cartoon helps to partially answer that question. Maybe we're here to have fun. Maybe we're here to help others have fun. And maybe we're here to explore. So next slide, please. Here we have Sidney Harris looking at least mountain climbing of an intellectual sort, of maybe a partially spiritual sort. And he thinks near the top is the understanding of this equation. Creation, no doubt, maybe that is Einstein himself there. But if we can just understand it, I think we'll be with the climbers on this mountain. By the way, after tonight's presentation, I will probably be the guy on the right there. Got a program to watch or two. All right. Next slide, please. It's no coincidence, I guess, that I have the same slide that David just showed you. This is from, I believe, January of 1945. And it raises a question about a quotation from Einstein that David probably partly already answered. Thank you. Thank you. Yeah. January 1946. Thank you. Yeah. So next slide, please. All right. Here is part of a quotation of Einstein. This was in 1945. If only I had known, I should have become a watchmaker. And I hope you will join me at the end of this talk to try to figure out what Einstein might have meant by this line. Perhaps it's obvious, but I'm not so sure. Next slide, please. Here's a mistake that I'm going to make as a speaker. I'm going to give you the three-word punchline, the three-word takeaway message for this talk. It's a sentence of three words: energy has inertia. But I hope to flesh out that statement to understand it fairly deeply by the time we finish tonight. Here is the paper. Does the inertia of a body depend upon its energy content? Good question, and I'm giving it away. The answer is yes. All right. Next slide, please. All right, so let's go through the three terms, the three factors, three expressions in this equation, and we're going to go from right to left, if you don't mind. I know that you know what each term stands for, but I'm a physics teacher at heart. Forgive me for that. I've got to make sure that each idea is fairly well grounded, perhaps even clear. Let's see. Slide, please. All right, so let's ask the question first: what is speed? Next slide, please. All right, there's a good old-fashioned equation, words instead of symbols, except for the equal sign and the division sign. Speed equals distance divided by time. It's how far you go in any given length of time. That is one's speed. And so we see a question in brackets there, the word dimensions. I'm going to be using this word dimension in the physics sense, not in the geometer's sense, as in measuring Earth geometry, not in the mathematicians, or no, how about this, not in the carpenter's sense. For dimensions to a carpenter, we've got length, width, and height. Right? Those are the three spatial dimensions that sometimes go by different names. But in physics, the word dimension is enlarged. We're not talking about spatial dimensions now. We're talking about physical dimensions. Length, width, and height are three types of distance, three types of, let's call it, let's say it's, distance. Okay, distance is a profound physical dimension. If you ask me to define distance, I can hold my arms out. I can say, well, think of lengths or height or altitudes or depths, but I have a real problem defining distance. So instead of that, I'm just going to say, at least regarding the dimension of distance, we're going to take that for granted in tonight's talk. Likewise, time. Time is a famously difficult idea to define clearly, but we're going to just pretend that we understand it. And time is also a fundamental physical dimension. It turns out that just three physical dimensions are necessary to characterize all of the basic quantities of classical physics. as opposed to, oh no, I shouldn't, Newtonian physics. All right, we need a third dimension to do all of classical physics. Sorry, a fourth dimension. So here too, distance and time. We'll introduce a third quite soon. But next slide, please. All right. While I can't define these dimensions properly, we can certainly talk about the units of each. The unit of distance we're going to use is the meter, about yay big, about as big as a yard. And the unit of time we'll use is the second, about the duration of one human heartbeat. So the unit of speed then will be the units of the numerator, distance, divided by the units of the denominator. In physics, we treat the units mathematically as we do the numbers themselves. So we have some numerical distance in meters divided by some numerical time in seconds. And so speed is going to be measured in meters per second. And 1 meter per second, nicely, is a very comfortable speed for humans. 1 meter per second is just about normal walking speed. Okay, if you're buying this now, I'd like to ask you to do a little, by a show of hands, perhaps, not a show, just raise your hand if you'd like to answer this question, but please don't say the answer out loud when you see the question. I'm going to ask you to estimate, in meters per second, to estimate a speed that you've probably been asked about before. All right, please estimate this speed in meters per second. But again, please don't say the answer out loud. Next slide, please. How fast are you moving right now? Okay, we got a few hands up. Madam, yes, please. It depends on your reference frame. Thank you, David, thank you. We got a problem here of relativity. So how fast are you moving right now? This is a question that has puzzled humans for thousands of years. Galileo seems to have been the first person to really understand the ambiguity of this question. We're talking about Galilean relativity now, not Einsteinian relativity. How fast are you moving right now? Well, I want to say relative to what? For instance, you might say, well, all right, the assumption is relative to your seat in this room, then your speed is 0. But someone will point out, but your seat is on a spinning globe, the Earth. And if your seat were at the equator, you'd be moving 24,000 miles roughly every 24 hours. That's a speed of 1,000 miles per hour. Hold on. You know, that's impressive. Now, we're not at the equator, but at our latitude here in the Bay Area, our speed relative to the axis of rotation of the Earth, our speed is about 800 miles per hour. Still, it's a good clip. And I'm sure you guys know that the Earth itself not only turns, it revolves around the center of the sun. So we've got a speed there. Oh, by the way, forgive me for using miles per hour in the last example of the turning of the Earth. Here I'm going to use miles per second. This, I'm told, the speed of the Earth relative to the sun is about 17 miles per second. Really cruising. And the sun and its retinue of planets orbit the center of the Milky Way galaxy. The Milky Way galaxy moves in the local group somehow. Local group moves relative to some cluster of galaxies, and so on. So we really have a problem here of we need to specify a reference frame. But wait, I'm an old school Trekkie. I have fond memories of Captain Kirk at the helm. Well, Captain Kirk as being captain, but at the helm would be Lieutenant Sulu. And Kirk would turn to Sulu and say, Sulu, what's our speed? And Sulu would dutifully reply, we're at warp 6, Captain. Now, we don't need to worry right now what warp 6 means, but what Captain Kirk never said was relative to what? Yeah, maybe it's the center of the galaxy, Milky Way galaxy, perhaps. But the question relative to what begs the notion of the question about moving through space. What is it? Can't we measure our speed moving through space the way we talk about the Enterprise's speed through the galaxy? The strange answer, at least still strange for me, is no. Space is not a thing. Ships, ocean ships, go through water. Airplanes go through the air. Spaceships don't go through space. They may go from this star system to Alpha Centauri, from point A to point B, but it's not helpful, and there's the bottom line, to talk about spacecraft going through space. Space is nothing. Space is not a thing. It's no thing. So you can't move relative to space. And what exactly the Enterprise, what exactly Lieutenant Sulu means when he says warp 6 is left beautifully unstated. All right, so we've got. Thank you, yes. That'll be the next presentation by David. Okay, let me see here. I am following, here we go. So that question, how fast we're moving right now, is answered, as so many of you said, by another question, relative to what? Now, we can summarize that by saying speed is relative. But I got to warn you that if someday you're pulled over by the CHP and the officer asks you, hey, buddy, do you have any idea how fast you were going? It is not wise to reply, relative to what, officer, right? Oh, all right. Let's see. If these ideas of good old Galilean relativity interest you, I urge you to check out a video online. Oh, next slide, please. We got to go through a few here. Sorry. I forgot that this is a team effort. Keep going. We're cooking. One more. There you go. Well, another one. Oh, no, here comes the joke. Relative to what? Okay. And now, here we go. This is a TED-Ed video. I think it's only 7 minutes long, but it's good at summarizing this idea of the relativity of speed. So if you enjoyed what you just heard for the last 5 minutes, check this out. It's a TED-Ed video, again, about 7 minutes long. Okay, let's see. Now, not yet on the next slide. At the back of every physics textbook, at least in the beginnings of courses, and perhaps at the back of many basic science books, for schools especially, there's a table of physical constants. Often they're described as universal constants. Please, next slide, please. Here's such a table. All right, and up top, sorry, the print's so small here. The universal gravitational constant, capital G, in weird units, a very tiny number. You and I don't have to know much about these numbers to realize that there is one number on this chart that seems like it shouldn't be there, or at least what's written about it is incomplete. It's missing something. Keep relativity in mind as you consider this universal table. Which item in this table, it seems incomplete in its proclamation of the value? Yes. Well, yeah, some like, for instance, acceleration due to gravity, for sure. Universal gravitational constant, as far as we know, has the same value everywhere. And we've not detected any changes in it. It seems to be universal and constant. But do you see a number up here that looks, given what we know about relativity, good old Galilean relativity, do you see a number up here that just looks like it's incomplete? Yes, sir. The speed of light. If there's any kind of number that shouldn't be in a table of constants, it's a speed. How can a speed be constant? Until that you fully understand what I'm saying, let's consider the speed of a baseball. I'm not a very good pitcher, but imagine that I were a good pitcher, that I could throw a 100-mile-per-hour fastball. All right, and I'm consistent. I always throw it at 100 miles per hour. So I whip it, it crosses the plate at 100 miles per hour. But I'd like to add a little speed to that. Nowhere on this chart does it say baseball speed 100 miles per hour. That's not a universal, even if it is constant. All right. It's not universal because if I wanted to cheat, if I wanted to do what is not allowed in baseball, which is to run while throwing the ball, right? The pitcher has to keep so far his, not her, foot on the rubber while throwing the ball. Because if the pitcher were to run at, let's say, 10 miles per hour, that's not very fast, 10 miles per hour while throwing a 100-mile-per-hour ball across the plate, it would cross the plate at 100 miles per hour plus 10. The speed of my run, the speed of the pitcher's run, would add to the speed that I normally throw at relative to the ground. And this would be a great advantage for pitchers, right? If you could suddenly, you're a 110-mile-per-hour fastball pitcher, you are a serious problem for all major league hitters. But it's not allowed. You got to keep your foot on the rubber because baseball's speed add to runners' speed. All right. Now, next slide, please. There is something very special about the speed of light, right? The speed of light is said to be invariant. That is, its speed does not depend on the speed of the thrower of the light, the speed of the flashlight or the spaceship. It does not depend on the speed of the observer, right? If the batter were dumb enough to run towards the pitcher, that batter would also experience an increase in the pitch's speed, but not so for light. And the trouble is, I bet everybody has heard this already, but I still think it's worth driving home because it is perhaps the most peculiar idea, as basic ideas go, in all of physics. Now, I've got a little demonstration here. When you guys are pointing out star groups or planets or astronomical phenomena to your fellow astronomers, or you perhaps folks crowded on your telescopes, you like to use the green laser. And there we see the laser dot because it's reflecting off of the cabinetry over there. But I've got some magician's smoke here, a completely safe medium really, that will allow the laser beam to reflect off its particles and see the beam as it travels. So I'd like you to take a look at this and then, yeah, it's nicer to picture, it's easier now to picture the beam. And I want you to think of my special device here at the end of my finger. Imagine that this is a speedometer for light. It's a light speedometer, so when I stick it in to the beam, it can measure the beam's impact speed on my finger. And I happen to have a fancy Apple Watch here. It's reading the 300 million meters per second. That's the number, 300 million meters per second. 7 times, roughly, around the Earth every second. This is a serious speed. And that's what I'm getting. But what I find is that when I move, as in the pitcher running towards the mound, running towards home plate, when I move the laser towards the finger, you got to trust me, 300 million meters per second still. And when I move the finger towards the source or away, no matter what I do, I always get the same speed of that beam of light right here. That beam, no matter who measures it, no matter how many times, no matter where, they always get the same number, 300 million meters per second. Next slide, please. Okay. Next slide, please. All right. What I've just said is rather extraordinary, right? This is a great quote. I think originally David Hume might have said it, but Carl Sagan massaged it a bit and made it more memorable. Extraordinary claims require extraordinary evidence. This is an extraordinary claim. Of all the things in the universe, when projected, baseballs, spit, planets, they all have speeds for which you must say relative to what when you get a number, but not a light beam. That's an extraordinary claim. And you know what? The evidence for it is outstanding. I've been told that there is no more directly and, most important, indirectly tested claim in all of physics than the invariance of the speed of light. That the speed of light of every beam at every point measured any way is always 300 million meters per second. So next slide, please. I do claim it's the most carefully tested claim in all of physics. Now, if that's true, if it really is an extraordinary claim, and it's rather basic, it's speed of all the things that shouldn't be weird. The mass of the electron, okay, that's weird. But the speed of something, the speed of light. Next slide, please. What further weirdness does C's invariance imply? All right, first, let's remember what that number is. Next slide, please. 300, 3 times 10 to the 8th, that's 300. 300 times 10 to the 6th, 300 million meters per second. Bear that number in mind. It's a very special number, and it's more than a speed. I can't say what it is. It's probably, as Lou would say, a ratio of special distances to special times. But I'm going to just say it's not a speed. It's more than that. So let's go on to the next slide, please. All right. C squared also. Remember, that's how we got started on this. C squared is also a very special number. It's more than its units tell us. By the way, let's go to the next slide, please. There it is. Okay. C squared is, remember, 3 times 10 to the 8th. So 3 squared is 9. Let's round that up to 10. And then 3 times 10 to the 8th, that's 10 to the 16th, times another 10, 10 to the 17th. Meters squared, I know what a square meter is. That at least makes some intuitive sense. But a square second? No. I would argue Einstein himself could not visualize, could not even conceptualize a square second. But he trusted the math. And in physics, you got to do to the units what you do to the numbers. Number is now for C squared 10 to the 17th, and the units are square meters over square seconds. All right, next slide, please. So we've made our way past the first of the 3 factors in this equation. The next, of course, is mass. All right, so next slide, please. And next slide. All right, first, remember these fundamental dimensions of distance and time. Next slide, please. There's another fundamental dimension called mass, a third basic physics dimension. And I happen to have, although I can't define mass very well, let's see. I can tell you what it's not. It's not the quantity of matter, right? It's not weight. It's related to each of those things, but mass is something different. To figure out what it is, how about if we look at any other equation that you might know from physics that involves mass? Next slide, please. All right, not weight, not quantity of matter, but what other equation, next slide, please. What other equation, dang, there it is. Force equals mass times acceleration. All right, F equals ma, there's m in there, and maybe we can use this equation to develop an intuition for the meaning of mass. It's force divided by acceleration mathematically, but that's not very helpful for at least for my intuition. All right, so let's suppose we have a standard unit of force. In the SI system, it's the Newton, properly. 1 Newton of force is roughly the force of a fierce blow of your breath. I just exerted about 1 Newton of force on my hand. Now, imagine doing that, applying 1 Newton of force to different masses and seeing what acceleration results. If I apply 1 Newton of force to a ping pong ball, I'm going to get, for 1 Newton here, I'm going to get a big acceleration for a ping pong ball. And that's going to make m a small number. Big denominator, moderate numerator, small number. Ping pong balls don't have much inertia. They don't have much mass. But if I try blowing on a bowling ball, or even let's just say a golf ball, roughly the same size as a ping pong ball, there, for the same 1 Newton of force, I'll get significantly less acceleration. The golf ball has more mass, more m, smaller denominator, bigger numerator, going to have a bigger mass for the golf ball than for the ping pong ball. Of course, you know that. To try to give that a little more heft, pardon the expression, how about if we try to remember this, that when you're measuring something's mass, use the wiggle test. Try to change its state of motion. For instance, I have here a unit mass. Next slide, please. All right. Mass is a resistance to changes. Big word there, changes in motion. Not resistance to motion, resistance to changes in motion. So when you want to sense something's inertia, try changing its motion. Try wiggling it. The wiggle test, next slide, please, is the best determiner of something's mass. Of course, it's not very quantitative, but conceptually, it really gets the point across. Notice I'm not feeling the weight. I can try wiggling this on a table with the mass here resting on the table, and then its weight is irrelevant. And when I try to shake it, this thing is hefty, it's sluggish, it's stubborn. That's what mass measures. Next slide, please. So the mass is a measure of inertia. Inertia, resistance to changes in motion, and its units are kilograms. This is a 1 kilogram mass, right? Now, I don't care, I don't know if you want to do this, but if you'd like to get a feel, that is partly what physicists go out, is understanding our feelings. Shake this, wiggle it, and see what you think of it as how you feel about it as a unit of mass. All right, here you go, just go ahead. I'd like this back, please. Yeah, but not up and down, shake it sideways, right? How much it pulls down on your hand is not the issue. That's gravity at work. This is how much resistance to you trying to shake it. Try to shake it fast. Man, it's a tough one. Okay. So we've got our second player in our little drama here. Next slide, please. We've taken care of C and C squared and M. Let's talk about capital E, energy. All right. Oh, next slide, please. And next slide. Maybe, as some physics and science books say, maybe energy is the ability to do work. I have no truck with that definition. It's not bad. It gets some of the difficulty of defining energy into words there. The ability to do work. What kind of work? Shaking that mass. How about homework, even mental work? The energy is involved in mental work. All right, so we've got this ability to do work. And next slide, please. I'd like you to notice that whatever E is, it's special. There is a department of energy. There's no department of momentum. There's no department of mass or speed, but energy is special. And by the way, energy is not a fundamental physical dimension. It's got very weird dimensions. Mass times length squared divided by time squared. But so what? So maybe the most important physical quantity in this universe is not a fundamental physical dimension, it's a derived dimension built from mass and length and time. Energy is very important, very special. All right, how about next slide, please? There are different types of energy. You remember this from your middle school, perhaps even, or certainly high school physics. There is, next slide, kinetic energy, then also thermal energy, heat, all right? Now, by the way, kinetic energy is the energy of motion. We'll go over this in just a minute. Thermal energy is also known as heat. It's the motion of tiny bits of matter, right? Right now, my fist is not moving. It's got no kinetic energy, but its particles, the molecules, the atoms of my fist are vibrating. Their vibration has kinetic energy of the atoms and molecules. Summed up, that's the thermal energy that's the heat of my fist. All right, next slide, please. We've also got potential energy here. Potential as in having the ability to do work quite clearly. Maybe not as clearly as I like, but we'll get there. Okay, now, there are other forms of energy that you've heard of. Please, next slide. How about light, sound, chemical, and nuclear? We'll talk a little bit about these as we go along here. All right, but I hope you ask, Tucker, what is the SI unit of energy? Next slide, please. All right, it's called the joule, right? The energy of one handshake, approximately, right? Up and down motion of your hand. To do that, you do about 1 joule of work. It's a nice, handy unit of energy, right? In esoteric SI units, International System, kilograms times meters squared divided by seconds squared. All right. Let me ask you, just so that we don't fill the room with a cacophonous joint shouting of names here. How about if you raise your hand and tell me another unit of energy that you've heard of besides the joule? Yes, sir. Ooh, yes. Sorry? One more time. Yes, horsepower. No, actually, that's actually power. Yes, okay, which is similar, yeah, but not quite the same. Yes. A calorie, excellent. Food energy is measured in calories for us normally. Any other units of energy? British BTU, the British thermal unit. I paid my close, but think about when you pay your PG&E bill, they don't charge you for megawatts. They charge you for kilowatt hours. Yeah, that's a bizarre unit because it's compound. It's built out of kilowatts, 1,000 kilowatts, and a unit of time. But those are all good units of energy. We're going to stick with joules though, because it's nice and, pardon me, handy, right? That energy of a single handshake, right? By the way, a watt is related to this. The watt is the use of 1 joule of energy per second, which happens to be about the power of a handshake. 1 joule every second, 1 watt. So when I gripe about paying PG&E, I pay them about 35 cents for a kilowatt hour of energy. But look at what that means. Next slide, please. All right. 1 kilowatt hour is 3,600,000 handshakes. This is for 35 cents. I still will complain, but come on, that's a good deal. And look at the energy in a calorie, 1 calorie, right? Every teaspoon of sugar, I'm told, is 17 calories, that's right. Look at all the energy at handshakes there is there. And then the megaton of TNT, yikes, 4.2 times 10 to the 15th joules. Yes? Oh, thank you. Yes, indeed. I understand that a food calorie is capital C. A little c is the more conventional calorie that chemists use, and that's 1/1000th of a calorie with a capital C. So a capital C is a kilocalorie for a little c, and that's what the chemists like to use is little c calorie. But food folks, and I do more eating than I do chemistry, like capital C. Yeah. Oh, is that right? Oh, okay. Yeah. Thank you. Yeah. Okay. There was another question? No? Okay. All right. This is the food calorie. Yeah. All right. Next slide, please. I'd like to emphasize this importance of energy. First, energy is good, whether you're a dancer, whether you're building a barn, or you're collecting sunlight and turning it into electricity. These pictures depict energy as in its good form. But next slide, please. There's also energy as harm, that is, as its destruction. We talk about perhaps the energy of a car crash. If you wonder why a knife is usually less lethal than a bullet, it's because bullets have more energy than knives. And all other things being equal, like where the knife hits and the bullet, where they hit the same area, the bullet does more damage because it's more energetic. And there's our kilotons of, perhaps even megatons there of energy being released. All right, so let's see. Let's go back to consider those types of energy. Next slide, please. Lots of types of energy. I'd like to draw attention to this guy right here. This is a very old can of Coke, Diet Coke, and it's diet not because it's low calorie, it's low joule. That's the way they said it in Australia, and I think they still do. In most of the world, energy is measured in joules, even lack of energy that you pay extra for, perhaps, in your soft drink. All right, but we've got light energy, we've got both kinetic and potential energy involved in this person's jump, and we've got electricity down there in the lightning bolt. All right, next slide, please. Here are the manifestations of kinetic energy that we see every day, the energy of motion. We got Usain Bolt with great kinetic energy, bullets, and people leaping off cliffs. Next slide, please. Here's potential energy. We've got gravitational potential energy of the woman on the tightrope. We've got elastic potential energy in the kid's slingshot there. And we've got both two forms of chemical energy in the apple and in the battery. All three forms here of potential energy. All right, next slide, please. And then I mentioned thermal energy, the energy, the sum of the kinetic energies are the particles that make up everything. All right, and here you notice you've seen these photos before because every photo that I showed allied with the harm in the destructive form of energy as harm. These are the same pictures because thermal energy is the most sorrowful form of energy. It's the one that it's the form of energy that energy attains at the end of time, both in the passage of every second and in what is sometimes called the heat death of the universe. So next slide, please. This is a nice way of remembering this, that thermal energy, that is also known as heat, is the graveyard of all energy. Where do joules go to die? They get thermalized. They turn into the random motions of atoms and molecules, and perhaps to other random motions of more fundamental particles. Okay, let's go to the next slide, please. There we've had it. We got all three terms fairly understood, and yet I still haven't addressed the idea of energy having inertia. Let's take that equation, and David hinted at this when he introduced this talk. Let's look at the next slide, please. Let's look at this equation and do a bit of algebra here. Okay. Yikes. I've got the basic equation, divide both sides by c squared. You see what's going on here. I'm just writing the equation in the way that Einstein might approve, as David said, where we're expressing the mass, the inertia of a quantity of energy. And there's that pesky little 1 over c squared, 1 over 10 to the 17th meters squared per second squared. Next slide, please. All right, so here is Einstein's great equation in its two different forms, completely equivalent. But I like to make this final sentence here that energy has inertia explicit, right? Make a calculation of how much energy. By the way, this verb has is interesting. You got to be careful to what physical quantities you use that verb to have or has. For instance, don't ever say that something has force. Things don't have force. A stick of dynamite doesn't have force. A stick of dynamite has energy. It's possessed by the atoms, by the stuff of everything. All right, so let's do a calculation here. How about we go to the next slide? Energy has inertia. All right, next slide, please. I've got promised to make this quantitative, and I will, but I'll make it kind of fake quantitative at first. All right, I've got an old-fashioned slinky here. It's kind of a small one, but notice the slinky is unstretched. That means the spring here has no excess potential energy, elastic potential energy. But if I do a little bit of work on the spring, maybe 1 joule, now I've added energy to the spring. And that means that if I compare, using the wiggle test, if I compare the inertia of this spring to the inertia of the stretched spring, yeah, I feel the difference. It's got more inertia. Maybe it does. All right. How about a dead battery versus a fresh battery? All right. Here is I was foolish enough to buy a Duracell D-size battery that had a D on it that didn't stand for D, the size. It stood for the fact that it's dead. This is a dead battery. And I shake it, and it's, yeah, I can feel that inertia. I use the wiggle test. I can feel it. And now I shake an energized battery. And I shake it. Oh, man, This is a good battery testing device. Maybe this battery just has a couple more joules of energy, but you can feel it if you're really good at the wiggle test. Maybe, maybe. Let's do one more fake example. All right. I've got here a magic box. The first demo involved elastic potential energy. The second demo involved, what was that? That was a chemical potential energy in the battery. Now I'm going to do a little demonstration with this magic box. It's not magic because it's beautiful, made of wood and metal, but it's magical because it's got inside, I've got aluminum foil in there. But what I want you to imagine is a box lined on the inside with perfectly reflecting mirrors. Perfectly reflecting. They don't absorb any light at all. Okay, so what? So I shake the box. Feel its inertia. Oh yeah, baby, that's maybe, I don't know, maybe 2 joules. No, sorry, that's the energy. 2 kilograms, that's the inertia, right? But now I'm going to open the box, shine some light into the box. Look at all the light reflect. It's all reflecting, but it can't reflect now. It's trapped, or it can only reflect inside the box. I've just trapped at least an extra joule of light in this box. It's bouncing around the inside, and I shake it. Oh yeah, I can feel that. Energy has inertia. I can feel the inertia of the extra few joules of light in this box. You know I can't, but yeah, I understand. And I'm not selling it, okay? But it's a beautiful idea to consider every different form of energy as having inertia, as having mass. So next, how much inertia does 1 joule of energy have? All right, in every case here, I imagine adding 1 joule of energy. Next slide, please. All right, what conversion factor takes us from joules to kilograms? Now, you've seen conversion factors before, right? Next slide, please. How about the conversion between distance in yards and length in feet? All right, if I give you a length in feet, no, first I'll give you a distance. To find out how far it is, a distance in yards and feet, you multiply by 3. D times 3, feet per yard, that's the conversion factor, will give you the length in feet. On the other hand, if I measure a length in feet and I multiply by 1/3 yards per foot, feet cancel, and I get 1/3 of a yard. A length of 1 foot is 1/3 of a yard. This is pretty simple. Do a D is 100 yards. All right, 100 yards, 100 times 3, 300 feet. Simple, right? This is a typical conversion equation in physics. All right, so let's try this with light. Next slide, please. We've got the 2 equations we just talked about, and we're going to compare those equations for energy and mass. In other words, we're saying that just as distance and length are 2 names for the same thing, energy and mass are 2 names for the same thing. Energy? Yes, that's a tough one. But here are the 2 equations. And so let's go to the next slide, please. What is the inertia of 1 joule? We're going to use our inertia equation. Here it is to calculate it. The conversion factor is 1/c². Next slide, please. All right, next one. There where we start with. Next. Good, there's old 1/c², incredibly small number because c² is 10 to the 17th meters squared per second squared, and this is the reciprocal of that. Next slide, please. All right, so I stick in 1 joule. Next slide. And now I've broken down the joule into its component units. A joule is a kilogram meter squared per second squared, and now I've got to multiply those units by the units of 1/c². And when I do that, next slide, please. Sure enough, there's a whole lot of canceling that goes on in this arithmetic, this algebra. And what I get left with is 10 to the minus 17th kilograms. Next slide. Whoa. Yeah, let's see. Let's do that again. 1 joule of light added here. Yeah, I can't feel that. You were so polite to listen to that. But clearly, in fact, next slide, please. The wiggle test fails to detect this puny mass. As far as I know, there is nothing that comes close. No inertia measuring device of this sort, doing the wiggle test, could possibly detect the inertia of a single joule. It's just too small. Okay, whoops. Next slide, please. Let's do the reciprocal conversion. We just took 1 joule of energy and said how much inertia it had. Now let's take 1 kilogram of inertia and see how much energy it has. All right, so next slide, please. Here we use the more conventional equation. We want to find energy in joules. We're starting with 1 kilogram, and there's good old C squared. All right, so sure enough, 1 kilogram. Next. The math is easy. The units are funky, but we're getting used to it. That's a joule. 10 to the 17th joules. Next slide. That's 100 quadrillion joules of energy. Next slide. This is serious energy. And what we're saying is that inherent in every kilogram of mass is 100 quadrillion joules of energy, just as inherent in every yard of distance is 3 feet of length. We're saying that energy and mass are 2 names for the same thing. The units are just different. Next slide, please. So 1 joule is the same as 10 to the minus 17th kilograms, but 1 kilogram is the same as 10 to the 17th joule. Notice we're not saying that 1 kilogram is turning into 10 to the 17th joules. No, they are the same thing. And so this idea that E equals mc squared, or its reciprocal, that it is applicable especially in nuclear reactions, just ain't so. It's true in stretched springs, it's true in batteries, it's true in light shining into perfect boxes. Next slide, please. So mass and energy are 2 names for the same thing. Yay. Look at Einstein's expression there. I love it. So here's the summary of tonight's key insights. Next slide, please. Energy has inertia, that is, it has mass. And there's the equation. And since that conversion factor is so puny, it doesn't have much. That's such a tiny number. Energy doesn't have much mass. Energy is of a human scale, the joule of a handshake. But mass has much energy. Here, the conversion factor is 10 to the 17th. And so we want to be careful with the energy inherent in every kilogram. I'm not saying I know how to thermalize it, but if I were to thermalize the energy of 1 kilogram, giving that 100 quadrillion joules of energy, that's enough to vaporize most of the Bay Area. Let's keep it in this form. Yes, yes. I did think it was Einstein, but no, not so. Whoa.
Yeah, that's how smart this guy was. And one of his optics things, he said something along the lines of, I suspect there's some sort of relationship and something about if you give something more energy. It's an amazing insight.
Huh.
He didn't have anywhere to go with it. And interestingly enough, when Einstein finally figured this out, he actually apologized.
Wow. Wow. Ah, and now I'll apologize to Einstein and to you for not knowing that. Thank you. Yes. Yes, I think so. And energy is mass. I prefer that verb to have, has. It seems like it's more expressive than is, but maybe not. I'm not sure that's right. We're just talking about good old English here, and I bet we can describe it different ways. Yes. What was the? Oh, I understand that in Latin, the word for speed, at least one of the words, starts with the letter C.
It's celerity.
Solarities.
That's where you get the word celery.
Ah,
Solar.
nice. Yeah, yeah. Good question, good answer. Thank you. All right, I've got one more thought here. Next slide, please. If you've enjoyed tonight's presentation, it's almost over except for our discussion about Einstein's state of mind when he said, I wish I should have become a watchmaker. I urge you to check this video out. In this case, what is it, about 17 minutes. It's part of a series called Radical Physics, and it presents this same idea that energy has inertia. So much of what you survived tonight, you can survive again, but in only 17 minutes. Think of the big plus. There it is. All right. This is a YouTube channel, and it is yours truly talking about this. All right. Let's see. In the next slide, we go back to that challenging cover for Time magazine. And again, next slide, please. This quotation from Einstein: "If only I had known, I should have become a watchmaker." Now, you know, as David told us, Einstein was not part of the Manhattan Project. He couldn't get security clearance. He didn't work explicitly in nuclear fission, which was a fission bomb that was developed by Oppenheimer and others at the Manhattan Project. So I'm wondering this is not a fake question now. I really want to know, what do you think was distressing Einstein so when he said this? Oh, after the bombs had gone off. Yeah. Yeah, I'm sorry I didn't show you the full quote, but that's only because I don't think knowing the rest of it helps. I think this was the crux. You know, I still call myself, and I was for many years, a physics teacher. I don't want to discourage kids from learning physics. This is discouraging. Yes. Ah.
By the way, Newton was also wrong about the amount of energy in relation to speed. He thought it was a linear function. Did not realize it was a function of the square of speed.
Oh, yeah.
So even people like Newton can be wrong.
Yeah.
Or maybe Einstein.
Yeah.
Actually, of course, Einstein was in some ways the founder of quantum mechanics, and yet he did not believe in his own child.
Yet I think of this as not being a statement of fact. It's a statement of Einstein's feeling, his state of mind. He was probably terribly disappointed at the devastation that these two weapons had wreaked upon these two cities in Japan. But he probably also realized that it did bring an end to a war rather much more abruptly than would otherwise have happened. Yes.
Understand the emotion during the war. But the Newton's purpose, but Einstein's assertion of the depth of the so it might be my understanding, but so far away from the actual bomb.
Yes.
Far away, like
Yes.
you cannot even connect the dots. It could be some dimensions.
Yeah.
So I don't. So from that point, I do not think.
That's why I'm asking this. I mean, on the one hand, you could argue that the theory of relativity did inform much of early 20th century physics, but it's a long stretch from E equals mc squared to nuclear fission. It's just, but yet here he just seems to be racked with guilt, and I want to understand it. I admire this guy. Yes.
Versus enormous amount of energy that is unlocked in nuclear fission when a small amount of mass is converted to energy. And so was the concept that so much energy is locked inside small particles that release them that might have inspired people to pursue
Yes.
fission.
Yeah.
And so he's looking at maybe, you know, the kernel of what they're pursuing is what he gave.
Yeah. Thank you. Yes. Yes, ma'am. Yeah, good point. Yes.
As opposed to a theory.
Yeah. Those physicists and engineers building the bombs use their hands too, but it's still, yeah, it's hard. Yeah, yeah, that's right. That's why this seems, oh, yes, David.
Well, I was going to say two things about this. First, Einstein wrote the paper in 1905. He did a lot of physics, like a ton of it. And there was a lot of discussion about what this actually meant, whether it was actually correct. And I forget who it was. It was a prominent English physicist whose name we all know. It was somebody like Eddington, who said the idea that you could use this to create an explosive is utterly ridiculous. There's no way that you could actually create a device that would harness this energy, which is intrinsic in mass. And when Einstein wrote the paper in 1905, we didn't know about the neutron. I don't remember when the neutron was discovered, but it was like 20 or 30 years later, because neutron carries no charge. And without a neutron, you could not have a thermonuclear or a nuclear reaction, a chain reaction. So there's a whole series of steps that had to be discovered before we could even create nuclear devices. And I mean, you can watch Oppenheimer the movie and then think about the whole idea of implosion. Rich, you want to make a comment?
Yeah, I think what's going on here is he perceived himself as being part of a club of brilliant individuals, and they're all kind of enabling each other through their progress in physics. And so he is kind of expressing part of a collective guilt, perhaps, over this. And it's not just an individual who is, oh, I came up with this equation and now I feel bad. It's more like this was his identity being part of this amazing group of individuals who together brought about this revolution in physics that unfortunately also brought about a revolution in weaponry.
Mhm. Yes.
I also like to say, I want to bring up the issue of Leo Szilard's letter at the time, because Einstein did play a critical role in the Manhattan Project. It may not have started if he had not signed that letter. He did not compose a letter by Leo Szilard. Leo Szilard was a Hungarian immigrant who fled Hitler, as many physicists have. And we all know that the thought was the Germans were way ahead of us. And there was this tremendous fear, understandably so, that Hitler would get the atomic bomb. I mean, some of the most brilliant physicists were working in Germany. And I forget who it was who, Otto Hahn, if I remember correctly, was the first one to get evidence for the splitting of glucose. And then Lisa Meitner, who was Jewish, had fled Germany and was in Sweden with another famous physicist. And she said to herself, I wonder if this is actually Einstein's equation. Is this actual evidence? And she did the calculations and came out right to her astonishment. By the way, there's another woman who should have gotten Nobel Laureate. And so all of this was set in motion. And then Einstein signs this letter, and it would not have got the attention it did from Franklin Roosevelt if it hadn't had Einstein's signature at the bottom. Einstein was very aware of that. And I think that's one of the reasons why he felt guilt about this.
I think the statement reflects enormous conscience. And back to your original statement, like immense claims require
Or extraordinary claims. Yeah. Oh, the years. Yeah. Yes.
well extraordinary power requires extraordinary.
Yeah. Yeah. I want to finish with just one more slide here. Please turn the next one here. Rather than think of nuclear weapons as being particularly proficient at turning mass into energy, let's try to remember this idea that mass and energy are two names for the same thing. That what makes nuclear weapons special is this, that nuclear events at the tiny level are 1 million times, typically around 1 million times more energetic than the chemical events. So when I talk about the energy in this battery, we're talking about the electrons near the protons and other charged particles in this battery. Those reactions, those intimate interplay of particles, those are all involving the electric force. Electromagnetic force is how it's generally described. But when we get into the nucleus, these are called chemical events. But in the nucleus, the nuclear forces can be involved, and they are typically 1,000,000 times more energetic per event than a chemical reaction. So turning mass into energy? No, a stick of dynamite doesn't do that any more than a nuclear weapon, but they both transform energy of one form into another, from, in a way, if you will, congealed energy into thermal energy. And that's the tragedy. Yes. It does. For sure. Yes. Yes. Well, you don't lose it. It's there in the heat that the reaction produces, or in the new potential energy of the products of the reaction. Yeah. Yep. Yeah. Yeah. That's right. And if you took a uranium bomb, a fission bomb, and exploded it in a perfectly energy-tight box, it would weigh the same before and after the explosion. It would have the same inertia. Yes.
So why is that number C so simple, like 3?
Well, 3 times 10 to the 8th.
No,
Yeah.
but it's not 2.96.
Oh, I believe it is. Yeah. 2.99. It's funny, the next 2 digits after the 2 are 0.99. And then I don't know what it is. Ooh, impressive. Yeah. Wow. Richard, do you mind going to the next slide here just so we can finish with a little plug here? This is a talk that happened last Tuesday at Wonderfest, trying to harness the nuclear energy in matter. And the talk was by a Cal professor of engineering, nuclear engineering, Per Peterson. He gave a great talk. Wonderfest is the Bay Area beacon of science. It's a small but bright beacon. And trouble is right now, it's not shining very much in the East Bay. If you know of any venue where Wonderfest could come, and I don't mean here, I'm not trying to, no, I love this. You guys, no, but and I appreciate you inviting me. The idea is check out Wonderfest. And if you can think of a venue as Wonderfest has in Marin, which turns out to have no charge. We have a room entirely to ourselves. And from the neighboring restaurant, you can order food and drink. If you know of any place like that around here, Wonderfest gives a benefit to the establishment because we bring in more customers, believe it or not, folks like you, and we give them a write-off because Wonderfest is a 501c3 nonprofit. So next slide, please. Here we go. Thank you for helping me climb that mountain tonight. Yeah. Oh yeah, please, I'm sorry, how impolite. Do you have questions? Or should I rather ask you, Richard? Should I hold questions privately or entertain questions?
we will certainly take questions. I would like somebody to volunteer for anybody who's
Well,
asking
I can do
questions.
it. Oh, okay.
I'll see if there's any.
Oh, good. Yes, yes.
I just want to make a comment. I like the wiggle test, but you need a spring with a much larger force constant.
Much.
I would suggest using a deuteron, okay, with just a neutron and a proton coupled together.
Yeah.
And then the work you got to do to pull those guys apart becomes the increase in mass. And if you then shake it, you'll
Yeah.
feel the inertia.
But it would only still be what, an MEV maybe? It still wouldn't be enough, right?
2.2 MV.
Okay, but that's that's nowhere near a joule. Yeah, I know I get your point. Yeah. Yeah.
It gets the idea because it shows that the work you do to pull the thing apart goes into increased mass. Rest part.
Yes.
It's less.
The heck with a slinky. Yes. Thank you.
So I liked your comment earlier about how, when you try to measure the inertia of 1 joule, it's so infinitesimally small that we can't measure it with our devices. Have we tried to measure the inertia of much more than 1 joule?
Yes, let's see how. There's much more, well, not much more than 1 joule, oddly enough, but this inertia of energy is tested every day at a place like CERN, at the Large Hadron Collider. There, particles wouldn't move the way they do when they collide them if this equation weren't right. That's one way I say that the invariance of the speed of light has, in a way, both directly and indirectly been tested so many times. If you want to earn a Nobel Prize, though, guaranteed Nobel Prize, if you can do a repeatable experiment that shows any beam of light moving from any source measured by any receiver as moving at anything but 2.99, whatever it is, times 10 to the 8th meters per second, yeah, you've got yourself a Nobel Prize. Yeah, yeah. In matter, when light slows down, as we say in glass or in water, it's slowing down as it is absorbed and re-emitted by the atoms. But in the vacuum between the atoms in glass, molecules in glass or molecules of water, there it moves at good old 300 million meters per second. Yeah, amazing.
But in those, sorry,
Oh, yes, sorry.
follow-up question, I guess.
Yes.
In those cases, though, the speed of light isn't necessarily changing, but the wavelength is elongating in that process when it's losing energy, right?
Right. Yeah, well, yes, the energy of a photon, a piece of light, moving at speed c depends on its wavelength, reciprocally on the frequency. Yes. Yes. HC, yeah. Yes, sir.
Energy has inertia, yeah, but also has gravity.
I've already gone longer than I should have, I'm positive. Yes, madam.
I asked earlier a little bit about mass equaling energy or mass having energy, or sorry, mass has energy is the same as mass is energy. And I was a little tough
Yeah.
on the semantics, but the bridge, it sounds like from what you're saying, is that it's that inertia thing that's the Venn diagram, you might say, where the circle of mass and the circle of energy completely are the same because of the inertia aspect.
Wow.
When you look at mass, it is a thing, right, for most of us. And when you look at energy, it's not a thing. So it's a little hard to grok that mass and
Mhm.
energy are the same.
Yeah.
So, but I think what you're saying tonight is that the bridge, that what creates that level of sameness, that merge, is the inertia potential, I guess, of the mass, or
Yes.
inertia of the mass. Does that make sense?
Well, yeah, and because inertia is more thingy, it's got thingness about it. Inertia resists your attempt to push it or slow it down,
Okay.
to wiggle it. And yeah.
And so if something like that is so, I don't know, I'm not a physicist, but if that was part of the obvious, part of what Einstein came up with and all of his predecessors, why is it a big deal to emphasize that now? Like something that people that are in this field don't know, or even really well-educated lay people.
I'm just going to hazard a guess here that to try to convince somebody that this spring and this spring have different resistances to vibration, different
Mhm.
inertias, that just seems so unintuitive.
Okay,
Yeah.
yeah, that makes sense.
Because we're used to mass being, as you said, thingy. It should have particles to it, atoms. Yeah, but that's not what it is. I can't say exactly what it is, but that ain't it.
And one more very simple question, it's totally unrelated. You said that the speed that we're going around is 1,000 miles per hour around the equator,
Yes.
and then about 800 where we are. So at the top of the earth, or is there any place where it's zero speed?
At the North Pole, I would make a circle like that once a day. So maybe, my shoulder is going faster than my heart, but right down my middle, there's, I guess, an imaginary line, as in good old Greek geometry, a perfect line right down my middle at the North Pole, the geographic north, where, yeah, there's no speed. Yeah. Sorry? Angular speed, yes, yes, as an extended object, but the axis doesn't have any angular speed. Yes. By the way, thank you for volunteering to move the microphone. I'm not doing my part by waiting until you get there. Thanks. Yes.
I was wondering, I've been kind of simplifying this in my head. And I don't think the math quite works at all, but if I wanted to explain this to somebody tomorrow, like, oh, I saw the school lecture, in like one sentence, like E equals mc squared is a conversion equation. And you wouldn't say like energy becomes mass or mass becomes energy in the same way that you wouldn't look at a foot and a meter and say like a meter becomes a foot or a foot doesn't become a meter.
Exactly.
It's just the same.
I really think that's a good way to do it. And that if you have to boil it down to 3 words, energy has inertia.
And then the Venn diagram you were referring to, it's not just an overlapping part. It's the same. It's
Well, I
two
think that's what you said.
circles
It's
overlapping
one
together.
circle. It's the
Yeah.
same stuff. Yeah. Since you are astronomers, if you'll allow me, Richard, I want to point out something challenging in that business of the speed of light being invariant. That is that there's no absolute frame of reference, no absolute frame of rest. I bet you all of you know about the cosmic microwave background radiation. And when we measure that spectrum, it's a so-called black body spectrum. There are lots of parts, many frequencies, it's all in the radio part of the spectrum, microwave radio. And the idea is that energy permeates the universe, right? We take our sensor, all right, the same sensor that was measuring the light beam from my laser here, and we point it in different directions. You always measure the same cosmic background radiation, except there are little differences with direction. From the point of view of Earth, the cosmic microwave background is not isotropic. There's a preferential direction. It's in a sense, you could say that the Earth is moving relative to the cosmic microwave background because there's a Doppler shift in one direction and an opposite shift in the other direction. So if we were to go to the reference frame in which the CMB, the cosmic microwave background, has no Doppler shift, would we finally find the absolute frame of rest? Well, I didn't know, but I asked Raphael Bousseau this question. He's a Cal, go Bears. He's a Berkeley physicist of significant renown, and I trust that his answer was accurate. And he said, no. That's the answer. While it is true that there is, in regard to the CMB, there's something special about that reference frame in which there's no Doppler shift, no red shift or blue shift, it doesn't give what Galileo and others have thought they wanted, which is an absolute frame of reference, God's throne. There just isn't any such thing. Even cosmic microwave background can't help us find an absolute frame of reference. Yep. Right. So you'd find an axis along which, relative to the CMB, we're moving. You know, because it's red shifted one direction and blue shifted in the other. But you'd think, well, let me just go to that frame where there's no shift, no Doppler shift in the CMB. And all that Bousseau was saying is, no, but that is not what we're seeking when we want an absolute frame of reference, so that Sulu can know what he's talking about when he says warp 6, Captain. Yeah. Yes.
Who first measured the speed of light, and how did they find out that it's invariant?
We already know we have a historian of science here. I know a little about it, but I'll bet you in another lecture, maybe you could talk about that.
Who said that? The way we first determined the speed of light was actually through astronomy. It was observing Jupiter's moons. And you could calculate theoretically when you should see the light and when you actually saw the light. And by timing that difference, you could calculate it was the amount of time it took the light to go from one side of the moon's orbit to the other side of the moon's orbit. And that was done by Romer. Thank you, Ernst Romer, who was Swedish? I can't remember. Something like that. And so that was the answer to the first part of the question. And how do we know it was invariant? I would say that's Michelson and Morley, wouldn't you?
Ooh.
You know, because, you know, they did all those experiments. I think they did get the Nobel Prize for their work, even though.
Right. Well, what I've heard is that Einstein was largely unaware of the Michelson-Morley experiment. Instead, what he relied on was to to be convinced that the speed of light is invariant, he relied on the principle of relativity, that is, that the laws of physics are the same in all non-accelerating reference frames. That seems not so dangerous. And he knew electromagnetism very well. He knew Maxwell's equations.
Yeah.
And if you're as smart as Einstein and you put those two ideas together, the principle of relativity, laws of physics are the same in all inertial and all non-accelerating reference frames, and Maxwell's equations of electromagnetism, you put those together and you're Einstein, you conclude that the speed of light must be invariant.
You
But
can,
notice that's where I started. I cheated enormously. Yeah.
you can derive apparently the theoretical speed of light from Maxwell's equations. I don't know how to do it, but I've been told that. So. Anyone else? Oh.
Oh.
Well, I guess there's something that sounds kind of dumb, but anyway, back in 1969, when I was going to Berkeley, well, one of my professors was Hans Einstein. See, and
Oh.
Hans loved to do laboratory experiments, you know, and well, anyway, he would watch the experiment and he would say, it knows what it is doing. And somehow those words echo in my ears over the years when I think of all of the things we're learning in science and everything, and it knows what it's doing.
And the it here is the it here is nature. Sir, the it is nature. Nature knows what it's doing, or light, both.
Sure.
Are you saying nature knows what it's doing?
What I recall, he just said, it knows what it's doing.
Okay.
That's what I remember.
All right. All right. Great. Thank you very much, and good night. Ooh. Forgive my mask wearing. I've got somebody in my home